Hello, this is Sean from MLabs, and this video is meant to assist with the review of the fifth milestone of the Purus Catalyst proposal. I'm going to do my best to respond to the concerns raised in response to our previous submission, though there are a few things I'm not entirely clear on what you guys were asking for in a few places, but I'll clarify that when I get to it. So as you can see, hold on this window. The acceptance criteria for this milestone basically consist of the tests and then some stuff on like documentation on a wiki website. So we have the documentation, which I believe should unambiguously satisfy the requirements. Here we have the comparison with other language. There's some technical documentation on using the compiler, including some notes on the built-in functions and ledger type declarations and stuff. You can't view this anywhere in a source file easily. It's baked into the compiler. Some of these primitive functions from the previous page, and then these ledger types, but these are all taken from pre-printed output of the stuff that's baked into the compiler, and we have instructions for installation and running the compiler and project structure, and I'm not going to go into too much detail over these things, though since you did request that we explain how to install the project, technically speaking, you don't have to install the project. You don't have to install the compiler, rather, but in order to run any of the tests or do anything with it, you're going to need to first install Nix, and you can follow the link to the NixOS website to figure out how to do that for your platform. You will also probably, if you are actually going to run this, want to configure a binary cache, which are just like pre-built artifacts that are needed to run the compiler. This should be pretty familiar if you're familiar with Cardano development, simply because Plutus uses this. I mean, to my knowledge, every single IOG product uses the Nix build system, and they presumably still have some documentation up, but it's been forever since I've configured a binary cache, and we use our own binary cache in MLabs, which you have to be an MLabs employee to access, so you'll have to figure out this yourself. If you don't do the binary cache thing, you'll end up building the Haskell compiler, which one time I accidentally did it. Takes, I think, 5-6 hours, and I have a reasonably beefy work computer, so if you want to run it, you may wish to do that overnight. Right, I would highly suggest that you configure the binary cache. And then the second step is clone the repository. This is the directory structure of the repository. I have a copy, obviously, since I'm the primary developer on the project. And then once you have the repository cloned, you enter a Nix development shell. And this is necessary to provide both some system-level dependencies that are peculiar to Cardano, and it also handles some other build dependencies. It's been quite a long time since I've looked at our Nix infrastructure, so I don't remember the details, but that should get you into a point where you can run the compiler. Cool. So, because the main thing that isn't just blatantly obvious with regards to the acceptance criteria is these tests, I was going to briefly go through the tests that we have, both the implementation, and I was going to run them. Fair warning, by the way, that I have a kind of minimal set of traces turned on for the tests. There are many, many more traces. The output that you'll see is not going to be particularly comprehensible if you don't have experience designing and implementing functional programming languages. And even if you do, there's a lot of things that are peculiar to both PureScript and Plutus. So I'm not entirely sure how beneficial this will be, but it will at least show that the compiler does stuff, right? And so the way that our tests largely work is we have a few different like test groups, but in general, there are two parts to our compiler, and we have tests that test one part and then the other part. And the first part is our modified PureScript compiler. So this in the repository you can see is stuff that tends to be located in source language PureScript, and this is our fork of the PureScript compiler, right? And there are a few differences, but generally speaking, our modifications primarily served to add type annotations to the abstract syntax tree that gets serialized. So the way the PureScript compiler works is it parses a file, converts into an initial concrete syntax tree representation, and then performs type checking and desugaring and a few other things, right? And it has the capability of serializing in JSON a core FN, their core functional representation, to a file. But in the ordinary workflow of an unmodified PureScript compiler, it will take the core functional representation, convert that to a core imperative representation, which is kind of like something that mirrors the structure of an imperative language like JavaScript, and then it'll transform the imperative representation into the JavaScript, because PureScript is a language that you obviously can, since we've done so here, adapt to serve as a backend or as a front end, I guess, for other sorts of target languages, right? But by default, most people use it for JavaScript, and that is what it is configured to do by default. There are variants that do other things. I'm aware of a fork of the PureScript compiler that serves as a front end for Nix itself, that build system, and I'm also aware of one that targets Lua, which somebody at IOG did in their spare time, which I thought was cool. So, and then our part of the compiler, the part that we wrote from scratch, is, if you want to look at the source files, in the language purist hierarchy, right? And it's primarily organized around the different transformations that we perform, right? So the first thing that we do is we read the core functional representation, we deserialize it, and then we convert it into a form that's more suitable for the transformations that we need to perform to translate this PureScript core FN intermediate representation into Plutus intermediate representation, or PIR, which is the intermediate language that the Plutus GX, the plugin for the Haskell compiler uses. So when it's translating Haskell to Plutus, if you're familiar with Cardano development, it's the stuff that you'll call that template Haskell compile function on, right? What that does is it translates the Haskell first into this Plutus intermediate representation, and then translates that, compiles that down into untyped Plutus core, or it might have an option to give you typed Plutus core. I don't remember, but at any rate, so we first read the core FN files, and we translate them into this intermediate representation. This is the type level for it. Where's the term level? Here. This is the term level for it, and this is parameterized by several different types. The first type that it's parameterized indicates the presence or absence of objects in the AST, where objects is the JavaScript way of referring to them, which is a little bit wrong. They're actually records, which are backed by polymorphic row types, right? And we use a kind of fancy Haskell library here to make this work for us. It allows for like fast and efficient operations in the AST, so like substituting for different variables and so on. And it has some structural features that provide some additional safety when we are doing these transformations, so we don't make a mistake, right? So that's the first thing we do. The second phase of our compilation pipeline is the inliner. And what the inliner does is it collects all of the declarations that are used in the main function that you're compiling, because the target here is a script, right? So ultimately our goal, and this is something that is perhaps different from other programming languages, which might compile something intermediate, some sort of intermediate bytecode or something that can serve as a library, but our goal here is to produce a Plutus script, an untyped Plutus core script specifically. So the inliner collects all of the declarations that are used and then performs inlining, which is where it replaces the identifier, or the variable that represents a declaration, with the body of that declaration. I don't know how much detail I really need to go into all of this. The inliner is pretty complicated. And then after inlining, we do a round of type instantiation, and this is the place where the row types actually get eliminated, or where row types, polymorphic row types, get instantiated to concrete rows, right? The lifting is part of the inlining. We do lifting as a necessary prior step to inlining, so I'm just including it there. Then we desugar the object. So this is where we translate these records or JavaScript objects into tuples, that is anonymous products, right? Then we finally do some stuff to eliminate case expressions. Because we use the data type declaration machinery of Plutus IR, you'll see what I mean when I run the tests. It generates data type declarations. Untyped Plutus core doesn't have data type declarations, but the intermediate language that we target as a first step does. And we need to translate these case expressions in pure script into into expressions that make use of destructor functions, which we have to generate the types and names and unique identifiers for. And then after we have eliminated all of the case expressions in favor of these destructor functions, we do the final compilation step, which translates our intermediate representation that we got in the core desugaring phase into PIR. And then not strictly part of the meat of the project, but after we get the PIR, we'll translate to UPLC, and then we usually evaluate it to force it to a normal form to give, doing so triggers some transformations in the PIR to UPLC compiler, which eliminate some unused expressions, so it gives you a smaller script. And that is the crudest possible summary I can give you of what the bulk of Purus does, right? And so the tests, you need to understand this at least a little bit to understand the tests. Test Purus. So this is the module that runs all of the tests that are particular to Purus, right? So the first set of tests that we have, these are we go through a few different phases where we test kind of each relevant step of the compilation process individually. So we have a directory, tests, Purus, passing, corefn, and this is just where we stash all of the test modules that we use. The first thing we do is we, in the test, try to compile all of these modules to corefn. So we invoke our modified PureScript compiler. And if that fails, then we don't continue generating tests for the declarations in that module because we won't have any declarations in that module, right? And then, so if that works, then we have PIR. And the first thing we do is just try to get to PIR without evaluating it to show that that works, right? And the second thing that we do here in the basic, these are kind of the core tests here, is we try to translate that PIR or compile that PIR down to untyped Plutus core and then evaluate it, right? And so for values or for expressions that evaluate to like a constant value or something, we can, and we do, I'll show you in a minute, check some of the outputs there to make sure that we're getting the return value from these expressions that we think we should. Right. So yeah, so this basically tests the full pipeline in and of itself, but there are some special cases that don't really fit into the infrastructure that we use to write this function that are handled a little bit separately. But this first group of should pass tests, it tests both the pure script part of the compiler and the modified pure script part of the compiler and the part that emits PIR, and it checks the translation to untyped Plutus core and evaluation of the untyped Plutus core, right? Okay, so the second group of tests that we have, these are expected result tests, and we should have more of these. However, due to the fact that that Plutus intermediate representation expects a globally unique identifier to be attached to each globally unique or locally unique too, I guess, variable, it's basically impossible to write out complex return types, or it's impossible to write out values of complex return types because very minor changes in other sorts of modules, like if we change the order of the declarations in our prelude module or something like that, will cause all of those unique indices attached to each variable, globally unique indices, to change, and there's not really a viable way of writing a bunch of these. So instead of having tests that examine a bunch of very complex values of complex types, we kind of just branch on them, and these are meant to target the cases that we think will most likely give us a mistake. So the other tests just check that something compiles, passes the PIR type checker, and then evaluates to something. These are supposed to be tests that cover the kind of strange edge cases that we want to make sure that things are actually evaluating the way that we think they are, right? And the expressions that we're checking the result of evaluation here for are in this miscellaneous folder. This is just where we put things. It's the largest single test module. It's 600 lines. And if you wish, you can examine the evaluation tests with their expected values and see if that makes sense to you. But they're definitely there. Okay. Right. I think those actually run last, but I'm just going through in the order that the do block does. And so then for testing the inliner, it's very difficult to come up with sophisticated tests that we know will trigger inlining for sure and that we expect to perform inlining in a certain way that actually terminate. Like the easiest ones, and many of the examples in the literature are like mutually or self-recursive functions that are non-terminating. Right, that means that if you're familiar with imperative programming, it's like they loop forever when run. And the point of having a separate group of tests here is that these expressions that we're trying to compile and evaluate, they won't ever terminate if we try to run them on like if we submit them to a node or something, that we'll get an error that they've exceeded the execution budget, right, or the execution limits. They have an infinite CPU cost because they never terminate. However, it's very important when writing an inliner and testing it to make sure that your inliner itself terminates. So even though these functions wouldn't be very useful on chain, they're very useful for us. That is the Purist team. And they're useful because we want to make sure that our inliner can handle inlining into functions that are perhaps infinitely recursive when we evaluate them. Right? We don't want the inliner to get stuck. We want it to be able to handle these functions and output a sensible Plutus core program that will run forever, but we want our compiler to not run forever here. And as far as we can tell, it does. So then finally, we have a simple batch of golden tests, which again refers to this MISC module, which is again the largest test module and contains a wide diversity of different examples that we intended to capture as much of the language as was reasonable given our time and budgetary constraints. And what these golden tests do is, due to the aforementioned issue with the unique indices, which eventually get translated into De Bruijn indices in the like PIR to UPLC compilation phase, but we could not figure out whether or not De Bruijn indices would be suitable before that. But because of this issue with the unique indices, right, it's extraordinarily difficult to come up with golden tests for anything that operate on our compilation pipeline after the point at which we started assigning these unique indices, because it's simply reordering the declarations in an unrelated dependency module, like not even changing their semantics, just copy and pasting one below another one that used to be above another one, will throw off that unique indexing scheme entirely. And so we did the best that we could for golden tests, and the best that we can realistically do is to have golden tests for the core FN, so the pure script part of the compiler, right? And this is kind of an unfortunate situation in some respects, but we could not think of a way of designing around it. It's just kind of forced on us by the choice of PIR with the requirement of these unique variable indices. So that is, given the constraints we have to work with, kind of what we're limited to, right? And then the should pass test, this just runs the tests. So I'm going to run the tests. First, I'll show you, are any of these modules worth looking at? Probably not. You can see the all of these functions point to a directory. So this, the make should pass test thing, we'll try to, what it will actually do is it will try to compile and evaluate every single function in every single module in this core level directory and test Purus passing, right? The goldens are just a copied over version of the output here pretty much, and that's to ensure us that nothing we do changes the core FN, because we shouldn't be making any changes to core FN. It's been known to be okay for quite some time now, right? And yeah, so I guess I'll very briefly go over what you're going to see in terms of the traces. This isn't going to be pretty because of the way that our testing, because of the way that Tasty works, the testing library that we're using in Haskell. I don't know the exact details, and it's not important for me to know, but it isolates various instances of running the tests from each other, but the output that you get is not like in any sort of coherent order. You'll see what I mean. For the traces, that is. I mean, it'll tell you whether or not the test pass. I forgot what I was going to look at now. Oh, right. I was going to show you the traces that I'm going to show you. So in language Purus make, this is the module of our additional pipeline that comes after the PureScript, modified PureScript compiler. And in this module, we have a function called compile. And this performs compilation. It'll either give you a string, which is an error, or a Plutus intermediate representation term, right? And so it basically just runs the functions from the pipeline that I explained earlier in the video. And the traces you're going to see are from this. And it basically just prints the result of the transformation after every interesting transformation. Some of these are not incredibly exciting, and for a large majority of the test cases, the outputs, like these transformations won't do anything because they aren't they all have conditions and requirements for triggering certain changes. right? So like the thing that instantiates types and applies polymorphic row arguments only does something if there are type variables that need instantiating, and quantified type variables that need instantiating, and you can't apply row arguments to a type that doesn't contain any row types, right? So with that being said, and again, so you'll see like the result of lifting, the result of inlining, the result of instantiation, object desugaring, nested case elimination, and full case elimination. Nested case elimination translates multiple scrutiny case expressions into nested case expressions that only contain single scrutinies, because PureScript supports multiple scrutiny case expressions, whereas Plutus does not. And it also handles nested applications of constructor patterns in pattern matching expressions. I can actually show you what I mean by that if it makes a difference. So in tests Purus passing misc lib. So by nested constructors in pattern matching contexts, I mean this, where you have, instead of just maybe int, you have maybe int. And this is something that is not directly supported by Plutus, but I mean, in the way that Plutus represents and handles case expressions is quite distinct from the way that PureScript does, so it doesn't really make sense to speak of this being supported in Plutus. But we need to make sure that we can compile something like this down to something that works in Plutus, even though this nesting here is something that wouldn't occur directly like this in Plutus, right? Okay, so I can run the test. If you want to run the tests, you just do cabal test when you're in your Unix development shell, and it's going to rebuild the project for some reason. And yes, now you're getting output. So here, I'll just walk through one of these to show you. I think I turned off the thing that tells you which declaration it is, but oh, this is for the testing an infix tuple 2 constructor, basically, right? So first we do lifting. Oh no, I lost it. Okay, I'm gonna have to do a different example. I think I'm running out of terminal space. You get a massive amount of traces when you run these. I'm not gonna be able to find that again. Okay, so this is something that's really, really simple. This is too simple, actually. I need to show you that it's actually doing more than that. This one will work, I think. Okay, so this is compiling, and this is, we only do compilation to PIR once, so we compile to PIR, right? And we note that as a success if it works. If we don't get any errors, and then we try to compile to UPLC and evaluate. And we don't have traces for the compilation to UPLC and evaluate because that all uses just IOG functions that are built into the Plutus library. It's not really something that we could fix even if it were broken, but it's not broken. So here, this is, if this doesn't get buried again in a mass of traces. So this is in the MISC library that I was showing you earlier, and this is these are the steps that occur when we're compiling this function, right? Cool. And I mean, you can look at this yourself if you want to see. It doesn't. It's not a function that does anything particularly useful. It's just no. I lost it again. Okay, never mind. I'm going to wait for this to finish. It'll just be another minute or two because I'm losing everything. These are, oh, actually, this isn't a terrible thing to look at if it didn't disappear. One sec. Okay, sorry. I have to wait for these to finish and then see how far I can scroll up because the traces, even with only a few traces enabled, we get so much output that it overflows my terminal's history, and I have my terminal history set to like 50,000 lines, so it gives you a lot of stuff. sorry, I just need to wait to make sure that I can get something that you can actually look at that isn't going to vanish into the ether. And since we're compiling 500-ish functions, and since it gives you all of this output for each of them, yeah, it can get pretty massive. Okay, I don't think anything else will throw a bunch of traces. So let me scroll up just so I can show you. So this, what you're looking at right here, these are functions that deserialize the script context, right? Sorry, I needed to check that my recorder was still working. These are functions that deserialize the script context, which is one of the major inputs of a validator. So if you're seeing all of this, this is probably one of our test validators, which are fairly simple, but show that you can we can generate code that successfully deserializes the script context and uses a bunch of Plutus built-ins to do so, and it's so long. May be difficult to, let me try to do this. No, that doesn't work with the terminal emulator I'm using. Sorry, I apologize. It is difficult to get nice, succinct, readable output from all of this. So let's see what we're working with here. And I'll go through, I believe it's stopped, and I can actually go through an example. This is a massive function. The function that deserializes the script context has to use basically every single deserialization function for a particular ledger type. So these are all going to be absolutely gigantic, right? And what you're seeing here, I can tell because it's printed differently. This is our intermediate representation that's being printed in some intermediate transformation between the PureScript core FN and Plutus intermediate representation. But until I reach something that tells me what step of the pipeline we are in, I'm not going to be able to tell you where exactly we are. Okay, so this giant thing that I've been scrolling through for like 5 minutes is the result of case expression elimination, right? So, this is a type abstraction. This thingy here, it means type abstraction. I don't know if the pretty printed representation of this is documented anywhere, but it should make sense to people who have seen other languages like this. It's pretty similar to what Plutus itself does. And so you can see, I'm just going to illustrate this as an example because going through this entire thing would take multiple hours. So you can see this here, this match Boolean function, right, with this type application. This is the result of desugaring a case expression or eliminating a case expression. So as I was saying, I'll scroll down to the bottom and show you this, but I won't be able to get back here, so I'll do that after I'm done showing you. So as I was saying, we use the Plutus intermediate representation data type declaration infrastructure. We could work with sums of products, but doing it this way triggers more optimizations as far as we're aware. So we can tell, though I cannot tell you what exactly in which source file it corresponds to. If you run the test yourself and set your terminal history much higher, you may be able to scroll up and find the declaration. It has to be one of the test validators. What we're doing here is this was something that was originally probably like an if-then-else, quite likely like an if-then-else expression in PureScript. That was through a series of transformations translated into a case expression because the PureScript compiler desugars if then else into pattern matches on Booleans, right? And then we translate that pattern match on Booleans into an application of the destructor function for the Boolean type we defined. We don't use the built-in Booleans mainly for the reason of handling everything consistently. This allows us to treat Booleans the way that you would normally treat them in Haskell, right, as an algebraic data type. So yeah, this is the result of our case expression elimination machinery that transforms what was once an if then else and then was a pattern match on a Boolean into an application of this destructor function. And here you can see this number here, this number 564 refers to the unique identifier that we have to generate. This is the thing that I was complaining about earlier that makes it really, really hard to write like tests for things that return complex values, because everything that has a name, you can see like here, and this is a type variable A, is also tagged with a unique identifier, and very small changes that seem superficial can completely change the particular identifier that's attached to something, and there's no way to deal with that except go through by hand and rewrite them all every time it changes, and we don't have enough time to do that. So yeah, and you'll probably see if you were to scroll through this, like this match script context. So this is the destructor function for the script context data type, right? You'll see a bunch of them, and these are the at symbol here means that there's a type application. So the way that these destructor functions work, and this is for the tuple, but the way that the destructor functions work is they have a quantified type variable, which is conventionally referred to as out in the PIR documentation, right? And so we need to, in the course of eliminating case expressions, we have to figure out what we have to instantiate that out to, because we have to instantiate it to something. And the at symbol here, these are my way of pretty printing some of the applications that the type applications that we're using, type applications, type instantiations that we're using here. So the evaluation failures, by the way, are expected in the test. It's very difficult to artificially create a script context that is suitable, and we couldn't get actual testnet stuff to work with the dependencies that we have to deal with here, because we're wedded to a bunch of pure script dependencies. It should work fine in an external library, or not an external library. It should work fine. It definitely will work fine if you run this as an application after we finish writing the build system for the last milestone, but we don't have the build system done yet, so we're kind of stuck with this for now. One second, I want to try to find the data types to show you what I mean by data type declarations. So more scrolling. I apologize, I don't have a faster way to do this. I'm using a different window manager than I usually do, and I don't have the shortcuts that I would normally do to do this, because the thing I normally use doesn't work with screen recording. Again, I sincerely apologize that I have to do all of this scrolling. Should have just used the GNOME terminal. There's so much of this. Yeah, there's normally a much better way to do this. Okay, so here you can see these are the data type declarations that I was referring to before. And so these are for both ledger types, like types that are defined in the like Plutus Ledger API, I think that's called that now, package, right? And so you can see, because this is a very large like function that has to work on almost every single ledger type when it's deserializing a script context, you can see that all of the component types for script context are here. There are also some of our own types. So we define this Boolean algebraic data type here. Right, and we also define a set of tuples, which we use for like objects or records that we have eliminated. And that's, I think, all I can really say here. If you want me to, I can just let the video run while I run the tests without the traces, so you can see that everything does in fact pass, and I'll show you that the only thing I'm changing is to turn those traces off here. It's not the most elegant way to do it, but it'll work. It'll rebuild. Oh wait, here's where I was running things. Call test. And you won't get any of the interesting spew of output here, but it'll do the exact same thing as before. this is what you're seeing right here. This is the modified PureScript compiler compiling all of the files, this is the PureScript compiler compiling Purus files to corefn.prs, so the PureScript file, source file format. So it does all of that first, right? Because these tests don't exist due to the way that they're written unless this succeeds, the first step of running the modified PureScript compiler. And only after we've done that do we look at the output directories and then run the tests on every function in the modules that were successfully compiled. We would get errors here. So if one of these failed, instead of seeing like this eval and no eval stuff, you just get a failure if it failed during corefn compilation. And the tests that don't evaluate run really fast, so we compiled a PIR really fast. But the evaluation tests, as you can see, run a little bit slower. Well, on my machine, it only takes 3-4 minutes to run, but I think it would probably take longer if you were on like an old laptop. Yes, and so you can see what it's doing here is shows you the file path to the module that we're running the tests on, right? And again, above a minute ago, I just showed you the output of the running the modified PureScript compiler on those modules. And here you'll see this is the first we compiled a PIR without evaluating. And then here we do the evaluation. And so what we do here when we evaluate, you can evaluate Ludus intermediate representation, but we compile to untyped Ludus core and then evaluate that just to get a more realistic sense. The amount of time that this takes doesn't really correspond to how much time it would take on the chain, because we are also doing some conversions that wouldn't happen on chain from PIR. And so you can see that these are all of the functions defined in that test Purus passing corefn miscellaneous test project, right? So it compiles them all individually. Waiting. These are our, if we have example validators and minting policies in test Purus passing corefn minting policy and test Purus passing corefn validator. I think it's called that anyway. These are the non-terminating tests I mentioned earlier, where they're considered to have succeeded if they hit the execution limit that we set, or if they exceed the budget, because if they don't, then we assume that the fact that we get here and can evaluate them all at all is kind of proof that the inliner works, which is what they're actually meant to test. Expected results. Oh, we get a this should have been a warning from the very beginning when it was compiling, but I told you before the output gets jumbled. So that's our test suite. While it could certainly be better, and I would most certainly wish to extend it before we advised anybody to actually use this for real work writing scripts meant to be run on chain, I believe that it's adequate to the requirements that we laid out in the milestones. And yeah, if there's anything else you would like me to explain, please let me know. But I sincerely hope that this demonstrates that we have actually done what we said we've done.